everyone. This is the 21st lecture in the series Mathematical Methods for Economics, and the topic for today's session is continuity, the concept of continuity as used in mathematics. Specifically, we'll talk about continuity of a function at a point, and then we'll extend this concept to talk about continuity on an interval or continuity of a function in general. So the roadmap for today's session is going to be as follows. I'll start by giving an intuitive idea of what we mean by continuity, and we'll also go over some real-life examples, some real-life phenomena to illustrate what is or what is not a continuous function of time. Now, after that, I will lay down the definition of continuity, the formal definition of continuity. We'll also talk about the different types of discontinuities. In particular, I will mark a distinction between what is known as a removable discontinuity, and we'll distinguish that from what is known as an irremovable discontinuity. We'll go on to discuss one-sided continuity as well and the properties of continuous functions, and as and when possible, I'll throw in some practice questions so that you can test yourself in terms of your understanding. So let's talk continuity, and what we're going to do is we'll start with this little activity, and I'm going to walk you through a couple of graphs here, graphs of functions on my screen. And what I would like you to do is, I would like you to draw these graphs. You can draw them freehand on a piece of paper or whatever you like, or you can just draw them in your head and see how the drawing of the different graphs varies. So you can first draw, let's start here. So you can first draw this particular graph in blue here, which is on the top left-hand corner of this screen. And then after that, and you can always pause the video if you like, so that you can go at your own pace. Then after that, go to this other graph at the bottom right of the panel and draw this one. Just copy it the way it's drawn, freehand. And after drawing these two graphs, now here in the bottom panel is a slight difference. This graph has a sharp point, but this is just to illustrate that you can handle these graphs as well when we're talking of continuity. Okay, so after you're done drawing these two graphs, come to this one. So if you look at this graph, if you try drawing this one, you'll be first going over this part of the curve, this yellow curve. So you'll draw this part of the graph first. And then you see there is a jump here. So you jump and then you draw the second part of the graph. Now, if you've drawn all these three graphs, try and understand what is the difference between the graphs, the first two graphs that you drew, and the graph that is marked as illustration 3 here. So if you notice here, the difference between the first two graphs on the one hand and this particular graph on the other is that the first two graphs, let's go back to that slide, and these two graphs actually you can just draw them without lifting your pen or pencil off the paper. So it's like if you're drawing this particular curve, you just keep drawing it, and there you are. So these are examples of, these two graphs are examples of continuous functions where you can draw the graph, you can draw the curve without lifting your pen or pencil off the paper, which is to say that there are no breaks in the graph, there are no jumps in the graph, or there are no holes in the graph. Is that okay? And if you look at this particular illustration, on the other hand, here you'll see that in order to draw this graph, you will have to lift your pen or pencil off the paper. So when you first draw this curve, you will come, you can see how I'm traversing this curve with the help of the mouse here. And after you reach this point at x equal to a, you will see that there is a sudden jump. So clearly you can't move from this point at the bottom to the point on top without lifting your pen or pencil off the paper. So this is an example where the function is discontinuous at the point x equal to a. It's showing a jump in the graph, and because of the break, the function is discontinuous. So let us look at some other examples also. Now, if you look at this illustration, here again you can see that you're not going to be able to draw this graph without lifting your pen off the paper at x equal to b. So you'll reach this point on the blue curve, and then this point is not there in the domain. So x equal to b is not in the domain. The function is not defined in the domain. So to cross over from this side of the graph to the other, you will have to lift your pen off the paper. So this is also an example of a graph of a function that is discontinuous. Similarly, look at this example here. Here again, you're going to have a discontinuity, and specifically you have a discontinuity here at x equal to 0. Okay, so let's just summarize what we have talked about so far. We are saying that a function f is continuous if the graph of the function can be drawn without lifting one's pencil or one's pen off the paper, which is basically to say that when we're talking of a graph, a function that is continuous, we're talking of a gradual development in this graph, and we're talking of a properly connected graph where there are no sudden jumps, where there are no holes or there are no breaks. Okay, and if the graph makes one or more jumps, then we say that the function is discontinuous. So this is as far as an intuitive understanding of the concept of continuity goes. Now let's ask ourselves where exactly, before we move into the discussion of the formal definition and all, let's ask ourselves where exactly is this concept of continuity used, or how is the concept of continuity relevant in the context of some real world applications or economics in particular. So what happens is in economics and in real world applications, we very often examine some phenomenon, we examine the change in the phenomenon over a period of time. And if I'm interested, suppose I'm doing some economic modeling and I want to understand how a phenomenon moves with respect to time, how it changes with respect to time, then if I want to understand, if I want to talk about the continuity of this phenomenon with respect to time, then here I might want to bring in the continuity of the function, the underlying function that captures this particular phenomenon as a function of time. So think, for example, if we think of the height of a growing child. So here we can envisage a height function where we measure, the function measures height of a growing child as a function of time. Now, you can think of this intuitively in the sense that today, if let's say the height of a child is, let's say, 3 feet, then it's not going to suddenly jump to 3.1 feet or 3.2 feet without going through the intermediate values. So you can expect, when we talk of height, you can expect the height of a growing child to be a continuous function of time. It's going to change continuously with time. It's not that like you're going to see sudden jumps in the graph. You're not going to see sudden jumps in the height, because if you go from one height to another, you also have to pass through all the intermediate values. So height function here would be a continuous function of time. Now here, we just giving you an intuitive sense of things, just look out for jumps. That's all we have to do for now, and then we'll move to the formal definition. Now look at the second example. The second example talks about, it brings in the price of a burger at your local cafe as a function of time. Now, unlike the height example, the price of a burger at your local cafe need not necessarily be a continuous function of time. Why is that? Because there may be events that might affect the demand or supply of burgers, and because of these events that affect the demand or supply function, there might be sudden jumps in the price. So this need not necessarily be a continuous function. What we'll do now is I'll walk you through this question, and I'll bring in certain phenomena, and now let's decide whether these phenomena represented by functions of time represent continuous functions. So the first one here is a person's body temperature. Here again, I think if you've got the idea now, we're basically looking for jumps if possible. So here again, you can argue that, let's say, a person's body temperature is, let's say, 99 degrees Fahrenheit today. It can't just suddenly jump up to 100 or 101 without going through the intermediate values. Okay, so this would be a continuous function of time. The temperature has to go through all the intermediate values before reaching the new value that you are envisaging. Similarly, the distance traveled by a car would also be a continuous function of time. However, if you look at this particular phenomenon, where we are marking out the price of fuel, the price of petrol per liter at your local petrol pump, this need not again necessarily be a continuous function of time. Firstly, because price here would be a rational number. These days you have these digitized digitized machines where the numbers would typically that would flash on your screen would be a rational number. So you're not going to have the price take up numbers other than rational numbers. And also, again, there'll be events that will affect the demand or supply of petrol, and that might then cause sudden jumps in the price of petrol. So this, it may be a continuous function, but it need not necessarily be a continuous function of time. Okay, so based on this intuitive understanding, I hope the message is clear so far in terms of what we are trying to convey through continuity. Let's now see if we can translate what we have done intuitively so far, if we can translate this into something more formal. And for that, look at this graph here. So here I'm showing you this graph where clearly you can see from the graph itself that it's a continuous function of it's a continuous function. But let's suppose we are talking of continuity at a point. But let's just back up. So we have so far talked about a graph being continuous if there are no breaks in the graph. So that is to say, the graph is a nicely connected graph. It's a connected curve. So if we want to now talk about continuity at a point, let's say I want to talk about continuity at this point, x equal to a. So that would also mean that the points that I have around this x equal to a, the points on the graph that I have around x equal to a, those should be fairly nicely connected with each other. Now, what do we mean by that? So for this, we'll try and understand the behavior of the function around x equal to a. And that is to say that if I am close to x equal to a, then the value that the function takes, around x equal to a should not differ much from f of a, which is a value of the function exactly at x equal to a. So that is to say that around x equal to a, f of x must be close to f of a. And this then motivates the following definition for continuity at a point. A function f is continuous at the point x equal to a if f of x is close to f of a, and that is then bringing in the idea of the function being close, the points being closely connected. So the limit of the function as x tends to a is equal to the value of the function at x equal to a. So f of x must come close to f of a as x tends to a. So I hope that condition is clear. And in particular, so just to do things more systematically, in particular, we are going to demarcate three conditions that must all be fulfilled. Remember, they must all be fulfilled together in order for the function f to be continuous at x equal to a. Okay, and these three conditions are, this is just like a checklist, so I'll just elaborate on this. So first condition is that the function f must be defined at x equal to a, which is to say that x equal to a must be in the domain of the function. The second condition is that the limit of the function as x tends to a must exist, and here we are talking of a limit in the sense of a two-sided limit. We'll then move over to a one-sided limit concept of in the sense of one-sided continuity also in a bit, but right now we're talking of the limit as a two-sided limit, so this limit must exist. And the third condition is that the limit of the function, the limiting value of the function f of x as x tends to a is equal to f of a, the value of the function at that point. Now note here that all these three conditions, they are both necessary and sufficient for a function to be continuous at x equal to a. In particular, you can also note here that actually, it is just enough to check for the validity, because that's what many students also do. They just check for the validity of the third condition, because actually the third condition is already carrying the first two conditions within itself. It is already implying the first two conditions. How is that and why is that? Look at the third condition. The third condition, the statement is that the limit of f of x as x tends to a is equal to f of a. So the very fact that you're talking of the limit of the function which is equal to f of a means from the left hand side that the limit of the function does exist, so that the second condition is satisfied. And when you're talking of f of a, you're clearly implying that the function is defined at x equal to a. So the third condition already implies the first two conditions, and when you're doing problems, you can straight away just check for the third condition. But then it's also it's very situation specific, so there may be times where you just might want to go through each one of these conditions systematically. It's like a checklist, so you first see whether the first condition is fulfilled, then the second one, and then the third one. It just helps you go through things systematically, and also it looking at these three conditions separately also helps you be very clear about the different types of discontinuities, because when we talk about removable and irremovable, so there are there'll be one or more conditions of these from these three which will not be satisfied. So it is a good idea to know to check each one of these conditions one by one. Okay, so that is as far as the formal definition of continuity goes. Now let's do one problem before we move over to more visuals. So let's just see if if you have absorbed the definition and you can use it. So your function here is f of x equal to x squared minus 2x plus 3. So here you have to check for the continuity of the function at a point A. So the first thing that you're going to check for is a function defined at x equal to a. Now see, clearly this is this function that you have here, x squared minus 2x plus 3. This is a polynomial function which is defined for all real numbers. So it will be defined for x equal to a. So the function is defined at x equal to a. The first condition is fulfilled. Does a limit of the function exist as x tends to a? Yes, the limit is simply going to be, because it's a polynomial function, so you've done the theorems on limits, and the limit is simply going to be a squared minus 2a plus 3. And that you can see also fulfills the third condition, because this limit is exactly equal to the value of this function at a. Okay, so this function is going to be continuous at x equal to a. Let us now talk about different types of discontinuities, and again this leads us to the three conditions that we talked about a few minutes ago, and if any one or more of the conditions of this definition fails to hold, we will say that the function has a discontinuity at x equal to a. So I'll again throw in some visuals here, and these visuals are meant to illustrate the different types of discontinuities. In particular, we'll bring in the concept of a removable versus irremovable discontinuity also. So let's get started, and let's look at our first visual. If you look at this first visual, again, just keep the three conditions in mind, what we're going to check for. The first is whether the function is defined at x equal to a. The second is, does a limit exist? And the third is a limiting value equal to the value of the function at that point? Now look here. If you look at this graph, at x equal to a, this function is not defined. You have a hole in this graph, right? So this is a situation where condition 1 only is violated. There's no need to even move further in the definition to check for continuity, because condition 1 is violated, and this, and you can even see visually that this has a break. There's a break in the graph. So because of this, we have a discontinuity. And if we check, if we just go over the other conditions, so the second condition here, you see that the limit does exist. So actually, if x approaches a either from the left or from the right, it's going to approach this value here, which is given in the open circle. So the limit does exist, but condition 1 is violated. And this in particular is what we call a removable discontinuity. Now, why is this a removable discontinuity? It is a removable discontinuity because all we have to do in order to make this function continuous is to simply fill up this hole. So what do I have to do? I just simply have to appropriately just assign this particular value to the function, and I will cover this hole so that the function becomes continuous. So I basically, removable discontinuity basically means that I just have to appropriately define the function in such a way so that the function becomes continuous. So I hope this is clear. So a removable discontinuity here is happening, and it is occurring on account of condition 1 being violated. So keep track of these conditions, because the removable and irremovable concepts are related to which condition in those three conditions gets violated. Okay, let me show you another illustration. And here you have that, yes, the function is defined. If you notice here, the function is clearly defined at x equal to a. You can see this dot here. But it's nevertheless a discontinuous graph. Why is that? See, again, the limit exists. The limit of the function exists because if we approach x equal to a from either the left or the right, you're going to approach this particular value, which would correspond to the one in the open circle. But what is happening here? Why is the discontinuity arising? Why is this function discontinuous as per the definition? It is discontinuous because the third condition is violated, because the function, the limiting value of the function, which is this one here, is not equal to the value, the actual value of the function at x equal to a. But here also it's not a problem, nothing to worry about. This is also a case of a removable discontinuity. All you have to do is just simply redefine this function and bring this point here, so you cover up this gap, and there you are. Your function becomes continuous. So what we have done so far is we've shown you cases of removable discontinuities which are arising either because condition 1 is not fulfilled or condition 3 is not fulfilled. So the limit exists. So note the conditions, because this will keep things, you'll be able to keep things straight if you are doing things this way. In whichever example that we did for removable discontinuity, in the two examples, the limit existed. So limit exists, but the function is not continuous at x equal to a, either because the function is not defined at a, or the function differs from the value of the limit. So either condition 1 is not fulfilled or condition 3 is not fulfilled. So I hope this concept of removable discontinuity is clear to you. Right. Now let's look at the case of another kind of discontinuity. Now what do you notice here in this picture? In this picture, what we have here is that the function is defined. So here our a is x equal to 1. So the function is defined at x equal to 1. It's taking on the value 5, right? But the second condition is getting violated. The second condition in the definition of continuity at a point is getting violated. And what you see here, the limit does not exist. If you approach 1 from the left, the function approaches 2. If you approach 1 from the right, the function approaches 5. So this is a case where you have a jump discontinuity. So this kind of a discontinuity is called a jump discontinuity, where you can clearly see this big jump in the graph. And this is also a case where you have an irremovable discontinuity, which is to say that here removing the discontinuity is something which is not going to be possible, because you have all these points to take care of. So earlier in the removable discontinuity part, it was just a matter of shifting one, just appropriately defining the function, which was just corresponding to one point. But here, taking care of this entire jump is a far more serious problem. And this jump discontinuity, where condition 2 is violated, this corresponds to what we call an irremovable discontinuity. Let me show you another example of an irremovable discontinuity. Here again, you can see the function is defined at x equal to 1, okay, but the limit does not exist. So main problem is that the limit does not exist, and this is also an example of an irremovable discontinuity. Okay, now let's go back to the graph of the jump, the graph illustrating the jump discontinuity. Now see, here we have a situation where, yes, we have a discontinuity on account of the limit not existing, but this is actually corresponding to the two-sided limit not existing. Okay, so this actually, if you modify things a little bit, you see that you can actually talk of the right side limit being equal to the value of the function at the point 1. So even though the two-sided limit does not exist, we can see here that the function is certainly continuous from the right. If you just look at this part, as x tends to 1 from the right, you can clearly see that the limit is in this case 5, and that is exactly equal to the value of the function at the point 1, which is 5. So even though we can't talk of continuity in the generic sense, where we took a two-sided limit, we can still talk of one-sided continuity. In particular, we can say that the function is continuous from the right. So formally, a function f is continuous from the right if the limit of the function as x tends to a from the right is equal to the value of the function at that point. And similarly, we can even talk of continuity from the left, where the limit of the function as x tends to a from the left is equal to the value of the function at that point. And here you can see you have a step function here. Actually the black vertical line has gone a little haywire in the slide here, but I think you can get the drift here, that if you approach 2 from the left, the limiting value is this particular height, and that is exactly equal to the value of the function at this point, right? So this here again you have a jump discontinuity, but you can still talk of continuity from the left. So this is all we have for the first part of the 21st lecture. Thank you.